Hey, thanks, Larry, very much, and welcome, everyone. As Larry indicated, I've got the opportunity, and indeed it is for me an opportunity, to interact with design professionals, construction, contractors, code officials, to answer questions or find answers for some of their questions regarding cold-formed steel. And so Larry and I have sort of culled through some of those questions, and that's sort of the basis for what we're going to be talking about for about the next 45 or 50 minutes. And as Larry indicated, if you have additional questions that we don't get to, or some of the highly technical, into the minutia aspects of cold-formed steel design, feel free to email me. I will give you my email address and my telephone number at the end of the session. So let's begin. We know that when we design, we use the North American Specification for cold-formed steel structures, commonly referred to as AISI S100, developed by AISI. Also, we have a series of framing standards, the S200 series. These are great documents. They provide us excellent information on how to design, but they don't answer all the questions. And in some cases, they actually generate questions as we try to use these provisions. So that's sort of where we're going today, is address some of these issues. Let's begin maybe with the beginning, if you will. How do I specify a cold-formed steel framing member? And for that, we will look at AISI S201, or what's commonly referred to as the product standard. And I'm sure that if you've done any work in cold-formed steel, you've seen this product designator before, where we're going to have a depth of a member, which is 6 inches deep. That's the first number. Then I've got an S, which means that I've got these edge stiffeners or lips on here. If these lips weren't here, we would see this as a T, which would be a track section. The 162 is giving me the flange width, or 1 5/8. If this were a 2-inch flange, that would be 200. And then we have the minimum base thickness or minimum delivered thickness, which is 54 mils. This is a number that is sometimes, in fact sometimes, often confusing to some, because this is not the design thickness. So if you're an engineer right now on the program, this is not your design thickness. This is the minimum delivered thickness as specified, which is 95% of your design thickness, and that is per AISI S100. So that's the only little nuance to watch with this, is minimum delivered thickness, not your design thickness. Notice as we look at this designator, it begins to give us the geometry. It does not give us that corner radius. It does not give me the length of this lip. For that, S201 will have tables which will give those particular values. So using S201, we can define the entire geometry then of our cross-section. Also, as I look at this designator, it does not give me the yield strength of my member. Yield strength is very important to us as we deal with the strength of the member. We have known historically that if a member is 43 mils or less, we use 33 KSI. If it was 54 mils or greater, that was a 50 KSI. That's sort of been a rule of thumb in the industry for many years. But I caution you, be careful, because that not necessarily is what's going to happen. In fact, this is a photograph of one of the new residence halls on my campus here. They're in the process of building several new residences. And for me, it's fascinating because they're all cold-formed steel load-bearing. But these studs were supposed to have been 50 KSI material. Well, what they found out was that even though it was a thicker 68 mil member, it was 33 KSI material. So they had to do some remediation as they were moving forward with the project. And in fact, if you review the SFIA technical guide, the design data is given for both 33 and 50 KSI regardless of what this thickness is up here. So we can find the 97 mil section with both 33 and 50 KSI values listed. So I caution you, be careful. Make sure we know what FY value we've got. Also, before we leave this slide, I intentionally added these gauge dimensions in here. And I emphasize that nowhere will you find in an AISI document that 43 mils is equivalent to 18 gauge. The gauge numbers are historically something that we've used. In fact, I'm as guilty as probably everyone else when I start talking about cold form steel members. I'll start talking gauge maybe because of my age or whatever. That's just what we've done. But we've got to be careful because, one, the 43 mil is really the important number, not the gauge. And in fact, there is no definite definition for gauge. As we even move through the cold form steel industry, it will change. Because if we attached 18 gauge to 43 mil here, then I went to the SDI documents for deck, 18 gauge there is 0.045 because the deck manufacturers use a different design thickness for what they're normally calling 18 gauge. And in fact, they do carry the gauge numbers along with them if you're familiar with the SDI documents. In the AISI documents, we do not. Everything is based upon the mil dimension, not the gauge dimension. So we use it, but we've got to be careful how we use it. That's all I'm saying. S201, let's go back to this yield strength for just a moment. In S201, the 2012 edition, which will be activated or referenced by the IBC 2015, which is 2015 is coming on us very quickly. So S201-12 states, when specifying material use in structural applications, the material grade used in design shall be identified on the contract documents and when ordering the material. S201 then references S200, which states, as you think about the marking of it now, the individual framing members shall have a legitimate label. And on that label, two of the elements that must be on there is the minimum yield strength of that product as well as the coating. So as we move into 2012 versions of our framing standards, we will now have to designate on our members what the yield strength and the actual coating is. So this is something to think about as we move forward into the 2012 edition. So what's the yield strength? Another common question is the 95% T. As I just mentioned, this mechanical property, this thickness that's given on the label, the 54 mil, for example, or the 43 mil, is 95% of the design thickness. It is not the design thickness. So what that is saying is that I can send a product out that has 5% less thickness. And I've had more than one building official especially say, hey, aren't you guys cheating? But this is where we're at with this. The design thickness is the bare steel flat thickness, exclusive of any coating. Section A 2.4 of S100 tells me that the minimum delivered thickness must be 95% of T. The 95% T is really a quality control issue. We're trying to control that we don't have too thin a material out there. If you've got any familiarity, for example, with HSS sections, A500, ASTM A500, enables a plus or minus 10% variation in tolerance on thickness. Well, 10% was too much. So this 5% kind of controls that. So that's some of the basis for the 95% T. Also, as we look at design formulas then, they account for any corner or tolerance effects. And what I mean by corner effects is that when we form the section, we are stretching the material in that corner when we create that corner, that permanent deformation, if you will. And as we stretch the material, the thickness is slightly thinner. But because the equations are empirical, they address that. So we don't have to deal with a variation in thickness just because we've stretched that material a bit in a corner. But the key is keep in mind the difference between design thickness and the delivered minimum thickness, which is this 5% difference that we see here. So no, we're not cheating. Actually, what we're trying to do is quality control our product when we use that 95% T. So that's my tolerance on a thickness. Common framing that we see in cold form steel. The most common would be either the inline framing or the ledger framing. We will see specific requirements in the framing standards for inline framing. Today, the framing standards do not have information on ledger framing. They're silent, but we're beginning to work on that. If you're not familiar with ledger framing basically is framing my joist into the side or into the flange of the stud rather than come in over top, which would be the inline framing. So this has some advantages. Again, as I think about a load-bearing situation, I've got a direct load path right down through without having to work through an interface and the joist that's sitting in there. So as we look at the next slide, we're going to look at inline framing. Ledger framing is something in the future as far as standards are concerned in the AISI framing standards. So what is inline framing? What we're trying to accomplish with inline framing, first of all, let me back up. As a structural engineer, what I'm trying to do with my structural assembly is create a skeleton for the building. This skeleton is to transfer the load. For example, if I've got my floor load on this joist member, this joist then will transfer that load to this location at the support. Transfer it then to the stud moves it down. My goal is to move this load up here on this joist down to the foundation. And I need a successful load path to do that. So as I look at my inline framing then, the key as I think about inline framing is, what is that load path to move this load through the joist, through this interface connection down to that stud member? If this joist moves too much or too far this way or this way, now all of a sudden I'm having to engage the track section. The track section then would have to transfer the load if the joist is sitting over here, for example. The track section has to transfer the load from this location over to my stud. Well, we all know that these track sections are not very strong, especially as you load them in this direction as oriented. So therefore, what we want to make sure is that this joist member is close enough to this stud such that I get, again, this direct load path for this load that I've got here to transfer through this connection. So how close is close enough? Based upon testing, which is actually done at the University of Waterloo, we've got criteria, and it really depends upon where I put my stiffener. If I place that stiffener inside of the C-section, as we see illustrated here, then this maximum distance from the center of the joist to the center of the stud is 3/4 of an inch. If, however, I place my stiffener on the back side of the web, which is very common and much easier to do, obviously, then I really have two criteria. One is still the 3/4 of an inch from the center of the C-section to the center of the stud. But I have an additional 1/8 inch requirement from the back of the web to the back of the web. And again, all we're trying to do with either this provision or this limitation here is to ensure that I've got an adequate load path. If these tolerances aren't met, then that means I've got to design that track section as a load-bearing track. Well, this C-section by itself isn't going to do it. There is, however, if you're looking for design guidance, a CFSEI tech note that illustrates design concepts for this load-bearing track. So this is a good resource, and in fact there's a whole series of CFSEI tech notes. If you're not familiar with those, you may want to seek out the list and see what's there, because there's some good information there on the design of cold-formed steel members and connections. So that's inline framing, meeting these requirements as illustrated. And this information is given in AISI S200, the General Provisions document. Installation. We know that S100 has no installation requirements. However, the S200 series does. For example, AISI S200, which is my General Provisions standard, has a tolerance limitation on installation of my floor joist into my rim track. What this provision tells me is I need to have a gap. It doesn't stipulate a gap, what that size needs to be. But what I need is a space between the web of the rim track and the end of the C-section. Why is that? Because as we start walking on my floor system, for example, this member is going to move up and down. If these two are in contact and this member starts moving up and down, we have the potential of generating a squeak. And obviously we don't want a squeaky floor. So therefore, that is the reason for this tolerance requirement. From a design perspective, for engineers on the webinar, this is my critical dimension right here, because that's defining my end dimension for web crippling as I evaluate this joist. So this is one tolerance. Another tolerance, I've got an axially loaded stud here. So this is a load-bearing application nested into the track section, as we see here. Obviously, I've got a gap. But, again, recall what we said earlier. I need to generate a load path. That means I've got a axial load, a downward load if it's gravity load, snow load, live load, an uplift load if I've got a wind uplift situation. But in either case, I've got to transfer the load from this member ultimately down to the track to get to that connection to accomplish, again, transferring my load to the foundation to achieve my load path. So if this is a load-bearing member, what S200 tells me again is that the maximum gap between the end of the stud and the web of the track is 1/8 of an inch. 1/8 of an inch is actually based upon some research that one of my graduate students did. There's a master's thesis out there on that. So that's for the axially load-bearing stud. If I have a curtain wall stud, that maximum gap is now 1/4 of an inch. It's not as critical because with that curtain wall, all I'm doing is resisting the wind load that's acting on the face of this flange, and that load will transfer out over here and over here. So this gap really doesn't come into play, but the committee felt that we needed to give a gap value of some dimension. So the 1/4 of an inch, I'll be honest, is arbitrary based upon a committee decision. The 1/8 of an inch is based upon research. So again, these are installation tolerances that we find in the framing standard series, either S211 or S200. Other installation requirements, we can look to ASTM. For example, as we look at manufacturing tolerances, if it's a load-bearing member or a structural member, it's C955. If it's that non-load-bearing, it's C645. And in the way of installation requirements, we have either ASTM C1007 or 754. So again, these are other locations that we can find tolerances for installation and manufacturing of our products. What about plumbness? Well, if we review the AISI framing standards, we're not going to find a definition for plumbness today in those standards. However, if we reference the AIA Master Spec 5400, Section C3.3, we do find this verbiage down here, which says that this member, this stud, for example, has to be installed, cold-form metal framing, level, plumb, and true, maximum allowable tolerance variation, 1/8 of an inch in 10 feet. So this is giving me an out-of-plumbness requirement that is not in the AISI documents, but we can find it in the AIA documents. Gypsum. The use of gypsum always generates a lot of questions because do we want to use it? Don't we want to use it? Should it be used in the structural application? And it really boils down to engineering judgment. For example, in AISI S211, Section D4, there are specific criteria and design equations. So AISI does, in the framing standards, provide for me a means of calculating the strength of a wall stud in compression. So this is an axially load-bearing wall stud now, where I'm going to use the gypsum sheeting on both flanges now, on both sides, as a brace. So what that means is I could eliminate the need for some of that bridging if I wanted to do so. But what I've seen in talking with engineers is that the judgment they're using is generally this may be used for a single-family residential, but not for a commercial application. So even though we have a design criteria for axially loaded members, rarely have I seen it used, to be very honest with you. And it really comes down to single-family units. That means a smaller structure, maybe lighter load, so and more walls, so that maybe this is appropriate. As we look at bending, however, that's a different issue because my requirement for bending is not as stringent as what my requirement is for axial compression. And so what we'll find, and again, in talking with engineers and asking for their judgment, what I've seen is the wall board may be used to brace the compression flange because the bracing requirement is not as stringent. And this has been for both residential and even for commercial applications as well. So it depends upon what we ask that board to do. How strong must that board be? It has to be a stronger element for pure compression versus what we see for bending. And therefore, we find different criteria. In fact, in S213, AISI S213, which is the lateral standard, there are values for shear walls using gypsum. So even in a lateral system for my overall structural stability, there are gypsum values out there if I wanted to use them. From an engineering perspective, we learned steel design initially using the AISC specification. Then, all of a sudden, we open up the AISI specification and then we say, oh my goodness, what happened? Why is AISI different than AISC? I mean, it's a steel member, so why do we see such difference? Well, maybe to give some reasoning. One, the shapes are cold formed from flat sheets or plates. So I'm taking a flat sheet of steel and I'm bending it, which really means I'm permanently deforming that nice, pretty flat piece of steel. As I form my section, I am changing the mechanical properties of the steel. So no longer do I have the same mechanical, and when I'm talking mechanical properties now, I'm talking about a yield strength, a tensile strength, and ductility. So those three properties will change just because I'm forming the section. There are some standard shapes, we know that, as we look at, for example, the SFIA technical guide. We see a lot of standard shapes, but there are also proprietary shapes as well. And that's sort of the neat thing about, I think, cold formed steel is that we don't have to stay with these standard shapes, whereas with AISC, you're more looking at standard shapes. This is the biggie, thin material. As I look at cold formed steel, I am using thin material. That's one of the key attributes of cold formed steel. I can make a structure using lighter material. But as I work with this thinner material, I'm definitely going to have to consider the failure modes that result because of this thinner material. And again, for the non-engineers, when I talk about a failure mode, what I'm doing is designing, when I design a member or a connection, I'm designing to prevent failure. So that's basically what the AISI specification does for me. It enables me to size my connection or my member such that my member doesn't fail. So as I think about the failure modes because of this thin material, it becomes thinner. That means I've got to concern myself with local buckling and the influence of post-buckling strength. So this is the big difference as we think about an AISC type of geometry versus an AISI geometry or a cold form geometry. It's the influence that the thinness of the material has on the behavior, which ultimately then means on the design of my member. We talked about forming this section. If I take a flat piece of material and I want to understand the behavior of this material, and remember, when I design, I'm designing such that I control the behavior of this material such that some failure mode doesn't happen. If I were to take a piece out of this and pull a tensile specimen, I would get a stress-strain curve that looks like this. If you're not familiar with that stress, think of that as load. So how much load I'm putting on it. Strain is deformation or stretching the material. So this could be thought of as a load deformation curve for this flat sheet of material. Now, if I take this flat sheet and I bend it into this corner, we said earlier that my mechanical properties are changing. What that means is I no longer see this type of stress-strain curve as I saw in the flats. I now have a different stress-strain curve in the corner or different load deformation behaviors. So as I look at design, I need to recognize this difference in the behavior, and that's what this cold forming process instills in my section. Or if you look at SFIA tables and they tell you that they are utilizing the cold work of forming, what they are doing is recognizing that I've got an increase in the yield strength in this corner section. The AISI specification gives me a calculation methodology such that I can reflect in the strength of the member that I calculate that the corners have this increase in the yield versus what I see in the flat. So that's the cold forming process. We talked about the thinness of the material and its influence. What that generates then, again, if you're familiar with the SFIA tables and you look at the section properties, what you'll find is that there are section properties given, and when I say section properties, I'm talking about an area or a section modulus or a moment of inertia. So these section properties, you'll find properties for the full section and for the effective section. Now, in an AISC world, we only concern ourselves with the full properties. In the cold-form steel design, I've got to consider the effective properties, because this is how I reflect in my design the influence of the local buckling. What S100 does is enable me to calculate what we're going to call an effective design width. It's based upon the stiffness of the element, whether it's a flange element, a web element, or an edge stiffener. So that's what these three elements would do. A stiffened element would be the web element, for example. A partially stiffened element would be the flange of a C-section, and the unstiffened element would be the edge stiffener of that C-section, or it would be the flange of a track section. And what this effective width or design width does is enable me to incorporate within my calculations the influence that local buckling will have on my design. Without getting into the minutiae of engineering, if I look at the design of this section and I put a bending moment, I'm applying a load up here. That's going to throw compression into this member right here. If my load is small enough that I don't create any buckling in this flange element, then I've got an internal stress distribution that looks like this. Stress distribution, think of this as a measure of how much force is in this element right here. That's what this stress distribution is reflecting. I need to know how much force is in this element in order to design this section. So from an engineering perspective, I need to know the area under this stress distribution. Well, if I continue to load the member, ultimately it's going to begin to buckle and show this wave that I see right here. And as this wave forms, I move from this rectangular geometry to this non-rectangular cross-section as we see here. So what this is saying is, all of a sudden, I don't have the full capacity of the cross-section working for me. If I had the full capacity working for me, this would be a nice rectangular geometry, as I've got here. I don't have that here. So therefore, this full section, the full flange, isn't working for me. Or I have an effective section. If I continue to load this to where I ultimately reach a yielding condition, I'm going to have a very nice, distinct waveform in here, a buckling wave. This will be that stress distribution. Again, to define how strong that element is or how much force I can place on this element, I need to know the area under this stress distribution. Well, again, if I had no local buckling and the section was fully effective, I'd have a nice rectangular distribution. But I've lost capacity in that element because of the local buckling. Rather than try to calculate the area of this unusual geometry here, we use what's called an effective width. We simulate saying that this B times the thickness will be the same as W over this nonlinear relationship. So basically, this effective width, which is now a simulated rectangle, enables me to easily calculate the strength of this element right here. So that's in essence what we're talking about when we talk about the effective width. If I have a unstiffened element, again, at an ultimate condition, I'm going to have a wave formation forming in here, which means a full section isn't working for me. That means my stress distribution looks something like this. I'm going to estimate that strength by this effective width. So rather than use the full width in my calculations for an area or for a moment of inertia, I'm going to use an effective width that gives me the same area that would be under this nonlinear curve. So that's the concept behind the effective width equations, and this is why we see in the SFIA technical guide we have properties for full sections and for effective sections, because I do not have the full section working for me at its ultimate capacity. Web holes. We know we place web holes in there to pass mechanical and electrical systems through the wall or through the floor. Those are typically 24 inches on center. From a design perspective, what does that do for me? Well, from a design perspective, an axial loaded member, section D4, will give me the means of calculating an effective area. And I say D4, that is the S100. An effective area, again, where I'm going to reduce the area because of local buckling, as well as reduce the area because I've put this hole in here, or this punch out. For a flexural member, we're going to do a similar thing. For bending, I'm going to use an effective section modulus. I'm also going to have to reduce the strength if that hole is too close to the support, because it's going to reduce my shear capacity or my web crippling capacity. So web perforation provisions are given in S100, and they enable me to evaluate the strength of the member, recognizing both local buckling as well as the presence of that opening or that punch out in the member web. So doesn't local buckling reduce the member's capacity? Obviously it does. We've talked about that. How does the specification then recognize that? What we find is that there is an interaction between local buckling and overall buckling. Again, think of local buckling as this localized deformation in the section, as I illustrated on about 3 or 4 slides back in that flange. Overall buckling would be the entire member moving laterally. Think of a wall stud, for example, and I've loaded axially. It will reach a certain load point where it will just buckle or move laterally. Or if you want to have some fun time, take a yardstick and push on the ends of it. At some point, that yardstick is going to buckle or move laterally on you. That is overall buckling. So how do we reflect that? Overall buckling capacity is determined based upon the full properties. So that is why, as I look at the SFIA technical guide, I need those full properties that are tabulated. Local buckling, then, we're going to use an effective cross-section, or that effective width that we talked about a few moments ago. Or in an equation format, that is my nominal stress. That's a maximum stress that I can place on the member, at which point the member will fail. Because I've got local buckling, or because I've got a punch out in that web, I can only use a portion of the area. So rather than use the full area that I may be putting there, only a portion of it's working for me. Same thing with a bending member then. My F sub n is for the full section capacity of the member, but I'm going to reduce it by using an effective property. So it's these two properties here that are effective, that are also listed in the SFIA technical guide, that are important to us. Let's move to something else. Lateral wind resistance, whether it's wind or seismic for that matter. X-bracing. Common question is, should I be using X-bracing, or is there a better way to do it? Well, there's nothing wrong with X-bracing. It's a very economical solution, but we need to keep in mind there are maybe 2 advantages or disadvantages. There are obviously economical advantages. It's easy to install, and I'm not putting a lot of material out there, because the best utilization of steel is to put steel in tension, and that's what we're doing right here. But from a disadvantage, bulging of the sheets, when I put my sheeting material on here, especially if I'm placing these X braces on an interior corridor wall. I recall walking down a corridor wall once where I could see where every X brace was because of the bulging of the screw heads at the base of that connection. We also have an issue with a multi-story situation where, as we load this member or this story, the studs in this story will shorten a little bit. As they shorten, this strap will bulge. So we've got to deal with that, or it's a loosening of the strap during construction. How might we address that? Well, possibly straps can be installed by a panelizer under pressure. And if that's the case, then any gap will be taken out of in the track section, which will minimize any slack that might occur in that strap. Otherwise, what I've seen contractors do is temporarily tack or screw, if you will. Don't put all the screws in the bottom. And then after you put that next story in, come back, loosen the strap, and retighten it. So this is another way to do that, okay? Again, if you're looking for guidance on design of a strap brace system, SFIA has a technical note on that as well. What constitutes a member brace? Very important, because we talk about bracing. Cold form steel members are very light. Because they are light, they're flexible. Because they're flexible, they tend to buckle very easily. I need bracing. If I look at a floor system, I'm going to have sheathing attached to the top flange. Bottom flange may have sheathing or sealing, or it may not. If it doesn't, I need to provide a minimal amount of bracing on that bottom flange as well. So from an engineering perspective, For this C-section, I've got to brace both the top flange, which will be my compression flange, as well as I'm stabilizing that tension flange or the bottom flange of the member. Also, as I deal with bracing, I've got to make sure that I anchor that bracing because, again, there is force in that strap. That is part of my load path then. I need to provide a load path for that force to ultimately move out of that strap and into a system that will ultimately move it to the floor. So anchoring of the bracing is important. Criteria for bracing. AISI S210. Now we're dealing with floor and roof system design. There is what I like to call a prescriptive approach for the bracing of the compression flange, which we said was going to be sheathing. What S210 tells me that if I use a 3/8" wood structural sheathing or a 9/16 by 0269 steel deck with at least number 8s attached to 12 inches on center, I'm going to have an adequate floor system to provide stability for the top flange of that joist member or adequate diaphragm. For the tension flange, if I don't have sheathing attached, then I'm going to design that bracing member. And S100 will give me criteria for that. And we'll look at that in just a moment. Through the punch-out bracing, does it really work? And this is a question that comes up quite often. The issue here is I'm running my little bracing channel through the punch-out, which is very common, very economical. If I'm using a screw connection, I'm going to use my standard clip angle. Clip angle, however, may not run the full depth of the section. So therefore, keep in mind, when I load this member in, if this is a curtain wall, for example, so I'm placing wind load along this flange. That means this section is going to twist this direction. As it twists then, I'm asking this member, which is at mid-span or mid-depth of this section, to stabilize these flanges. Does it work? Well, based upon some testing I was involved with several years ago for bending now, which we felt was more critical than axial load, what we found was that for a 3 5/8" section and a 6" section, that assembly worked very well. The 8" section, it did not. So we need to think about our bracing as we look at bracing through the punch-out for an 8" deep section and watch that length of that standard angle especially. As we deal with member bracing, I mentioned a couple slides back, S100 gives me provisions in section D3. It tells me that brace needs to prevent lateral bending, twisting, and I can't have any local crippling at the attachment. What are we dealing with here? Well, when I say specification now, this is S100, does not address bracing for when I say singly symmetric section, that is a C-section. So for a C-section that's actually loaded as a compression member. So this would be my load-bearing stud system now. In this load-bearing stud system, if it's an exterior wall, it's going to see an axial load, and it's going to tend to want to buckle about its weak axis or buckle in the plane of the wall. And I'm also going to have some torsional flexural buckling of the section as well. It's going to bend. S211 now, because the specification S100 doesn't address this, S211 will tell me that for this combined bending and axial load, which is all this is right here, each brace shall be designed for the combined brace force determined by section D321 of the specification, which is S100. This is a torsional brace. And then 2% of the axial load. This is my flexural buckling as we talked about here. So I'm addressing both my torsion and my flexural buckling with this provision that is in AISI S211. It's not in the specification. As I design my stud, if I'm going to use an all-steel design, which means I'm not using the sheathing to provide bracing, I'm putting bridging members in, typically at 48 inches on center, for example. S100 gives me design equations to determine or estimate the strength that that member will have. Two parameters that are in that equation in S100 is a parameter K and a parameter L, which is the distance between my braces. So S211 tells me to use K equal to 1 when I'm evaluating my axial load in S100. S211 will also tell me For the unbraced length, for the X buckling, it's the distance between the end supports. For the Y buckling, the Y-axis, and the torsion, it's the distance between the braces. So again, S211 gives me definition for parameters that are not defined explicitly in S100. So that's sort of the progression of what we've got with these documents. S100 is my general design document. The S200 series then is helping me to define some of the parameters that I need in order to evaluate that general design equation in S100. So both of these documents working together enable me to adequately design my members. As I deal with beam behavior now, again, I'm still talking about bracing now. As I load this member will want to twist on me. For those of you that are engineers, think about the shear flow. I've got a vertical downward force. That means I have an upward force in the web. That's going to turn the corner, and I've got a horizontal force in this direction here and a horizontal force here, as illustrated here. These two forces will tend to want to twist this section. So I need to stabilize this section from a shear flow perspective. That F dimension then needs to be estimated. Well, section D322 of S100 tells me that that F, we're now going to call it P sub L, the design brace force, is given by these two equations. Whether it's a uniform load that I'm applying to that joist or whether it's a concentrated load, these are the respective equations that we're dealing with as we focus on shear flow, which again, all I'm trying to do, if we hop back, is stabilize this section from this twisting behavior. If I don't stabilize it, this C-section will not have much load capacity. So this bracing is very important to me. Screw connections, the most common connector that's used in light steel framing. From a design perspective, it's section E4 of S100 where we will find our design requirements. And, for example, that screw connection there, if this is a wall stud, axially loaded wall stud, for example, under a wind uplift, I've got to transfer that uplift force from this member through that connection into here. As we look at the behavior of this member attached here, I'm transferring load again. So any place I see a screw connection in light steel framing, I'm going to rely on E4 of the specification. So E4 gives me design equations for all 9 of these limit states. And again, for non-engineers, when I say limit state, how this connection or connector can fail. For example, that screw can fail in a shear mode, it can fail in a tension mode. Or the sheet can pull over the screw, or the screw can pull out of the base material. So all of these various limit states are addressed by equations that estimate the behavior or the strength in S100. New to the 2012 edition of S100 is an equation for combined sheet tearing and pull out. We've had one for sheet shear and pull over, but we did not have one for sheet shear and pull out. Well, new in 2012, we have that as well. So again, all I'm doing here is trying to prevent a failure when I design. Proper installation, though. The screw isn't going to work for me structurally if I don't have it properly installed. S200 now is going to give me some design installation requirements. For example, it's going to tell me that a properly installed screw, I must have at least a minimum of 3 exposed threads beneath my bottom sheet that I'm connecting. Also, no permanent separations between the plies, so this screw needs to draw these sheets together. Why 3? Well, because with self-drilling screws, sometimes we will have a taper from this drill tip up to where we get the full diameter of the screw. And it's the full diameter of the screw that I use when I calculate the strength. So we want to make sure we have that full diameter working at that interface right here, and that is really the basis for the 3 threads. Strip screws are always an issue. S200, will give me design guidance now. Strip screw fasteners in direct tension, they're not going to work for me. They're ineffective. I've got to replace it. But if I have a strip screw in shear, what S200 will tell me is, as long as not more than 25% of those are stripped, I don't need to do anything. For example, if I have a screw connection that has 4 screws. I can have one of those screws stripped and I don't have to do anything. I haven't lost capacity. That's basically what this provision is telling me. The basis for this information comes, again, from one of my master's students' thesis. So this is based upon testing. The spacing of screws. In S100, it tells me that I need to have at least 3 diameters spacing between screws. So center-to-center spacing must be at least 3 times the diameter. Now with the self-drilling screw, it's entirely possible to get screws closer than that. So what do I do then? Well, based upon research, again, that one of my students did, we found that if the screws got too close together, we lost capacity, as much as 20% loss of capacity. So again, S200 says if I don't meet this, I've got to consider a reduction in the strength of my screw connection. Many engineers use manufacturer's data. Nothing wrong with that. But how do we do that then within the specification? Section E4 is the only provision in the 2007 edition of the specification that says, hey, you don't have to use these equations. So this verbiage here is in Section E4 of the specification. What it says basically is, alternatively, design values for particular applications shall be permitted to be based upon tests. Those tests have been done by the manufacturers. So this provision here is what enables me as an engineer to use manufacturer's data instead of the equations in the specification. Where do I go to find more help? Well, this is a partial list. AISI, for example, this is their website. If you're looking for a design guide or the specification itself, they have a bookstore. This is a place to go. CFSEI, there's a hotline, in fact, that you can call or email, or go to their website as well. And the tech notes that I alluded to a couple times are found here as well. SFIA, their website offers some valuable information as well on the design of cold-formed steel members. This is the website for my center, the WeWin Center for Cold-Formed Steel Structures. If you're looking for a textbook, Dr. Yu's textbook is an excellent book on the design and the background of cold-formed steel. So these are some of the resources to where you can go to find additional information. Also, this is my direct email and my direct telephone office number. If you have additional questions in the future, please do not hesitate to contact me, either via email or leave me a voice message if I'm not in the office, and I will get back with you just as quick as I can to try to help you.